Hello, classes. This is your teacher, Miss Thede, and I hope you are doing well. Glad you are here today, or if you're not here today, at least that you're watching this video. I would ask that you would copy down the notes and also listen to the video and watch what I do as I go through the bell work and the notes for today. So let's go ahead and get started. So we are on page 6. We're looking at bell work day 12. It says, using the table shown above, calculate the following probabilities. Well, it's actually down below, and you probably figured that out. All right, so letter A says, what is the probability that someone ordered pizza given that... There's that conditional statement again with the vertical line, given that they ordered water. Now, you might not remember, but whenever you have a conditional statement followed by some item, that item becomes your new probability. So I want to look at all people who ordered water. So find my water. Here, all people that ordered water, that's going to be over 140. Okay? So whenever you have a conditional statement, whatever follows that vertical line always becomes your new denominator. So then I need to look at the intersection of all the people who ordered pizza and water. So here's my water column. I find my pizza and where they intersect, that's going to be 58 out of 40, 140. Oof. So if I wanted to write this out, it's the probability of pizza and water, that's an and statement, all over the probability of water. But this is the answer we're looking for. All right. Now, letter B is not a conditional statement. It says, what is the probability that someone did not purchase a drink or no drink and had a hot dog? Okay. No drink and a hot dog. Since it is not conditional, we know that the denominator is going to be what I call the total. So that's going to be 400. This is my and statement. So I'm looking for the intersection of no drink and a hot dog. And where those two cross is going to be 46 out of 400. 46 out of 400. And the last one, I'm going to clear this table just so it's a little bit easier to read. What's the probability that someone did not get a drink given that they had a hot dog? Okay. Well, like we said before, that is the probability that someone did not get a drink and that they got a hot dog all over the probability that they got a hot dog. So this is a conditional statement. There's that vertical line. As soon as you see that, boom, that's your new denominator. So hot dog, find the total for hot dog. That means it's going over 158. And I want the intersection of no drink and hot dog. So the numerator is going to be 46. So for letter B, the probability that someone did not get a drink and got a hot dog, that's out of everybody that bought anything from the concession stand. That's why my denominator was 400. But in letter C, we wanted the probability that someone didn't get a drink given that they purchased a hot dog. So that's why hot dog numbers, the total, which is 158, was put on the denominator because we're looking at only those who did buy a hot dog. So that's the difference. All right. I think that's it for number 1. I'm just checking here. Huh, that's interesting. Maybe you didn't have a letter C. It's on here, but it's not on my old paper, but who knows? All right, let's take a look at number 2. A football coach has 3 quarterbacks, 6 wide receivers, 7 defensive linemen, and a kicker. So be careful and make sure you read the whole thing. Don't just look for numbers because the kicker is in there, but there's not a number in front of it. Hopefully you recognize that a kicker would be 1 kicker. 1 player got hurt. What is the probability? So we're looking for a probability that it was one of his quarterbacks. What's the probability that it was one of his quarterbacks? So remember, probability is the number of successes in whatever it is you're talking about out of the total number. Number of successes out of the total number. Okay? So my total number would be adding these up. So I've got 3 quarterbacks. I have 6 wide receivers, 7 defensive linemen, and a kicker. 3 plus 6 is 9. 9 plus 7 is 16. 16 plus 1 is 17. That is my total. That total number goes in the denominator. Okay? Now, it's a probability, so it's got to be a numerator over denominator. I have my denominator. The success is that they want to know, was it one of the quarterbacks? Well, for quarterbacks, there are 3. So the probability that it was one of those quarterbacks, the success that we're looking for is the number of quarterbacks we have. So it's 3 out of 17. Okay. So you can go back and look at this as often as you'd like, since this is a video, but we are going to move on now to our notes, and we are on page 20, talking about our last section, and that is 7.4 independence. Now, I've talked about this some briefly. We're way down here. Here we go. Talked about this briefly, but not in the context that we're going to talk about it today. Talked about it kind of that, in that does doing one thing affect another, or are they independent? Okay. Well, this is talking about independent events again in a little different way. So first of all, let's come up with a definition. What are independent events? And this is pretty basic, but independent events are events that have no influence on each other. Independent events are events that have no influence on each other. All right, so how can we test for independence? And this is the item that's a little bit different from what I've been talking about before, okay? So if we have a probability of A and B, and that's the AND statement, right? And it is equal to the probability of A times the probability of B. So if I look at this intersection of A and B, and it equals the probability of A times the probability of B, if they are equal, then A and B are independent. Okay. So let's see what we're talking about here by doing some examples. So it says for number 3, the probability of selecting a purple marble from a bag of marbles is 0.4. So the probability of picking a purple marble is 0.4. And the probability of selecting a big marble from the same bag is 0.55. So the probability of getting a big marble is 0.55. The probability of selecting a marble that is purple and big, remember that and is the upside down U, is 0.3. So the probability of purple and a big marble is equal to 0.3. Are the events selecting a purple marble, this one, and selecting a big marble, are they independent? Well, according to what we just saw in number 2, we need to take the probability of both and see if they are equal to the probability of each of those items separately. Okay? In other words, is the probability of A and B, is that equal to the probability of A times the probability of B? Okay, so is the probability of the purple and the big marble, is that equal to the probability of purple times the probability of the big marble? All right, so the probability of purple and big, they said, was 0.3. And this is all something that we are trying to find. Is it equal to each other? Well, the probability of pulling out a purple, they said, was 0.4 times the probability of a big marble is 0.55. So is 0.3, is it equal to 0.4 times 0.55? If you multiply those together, you're going to see that we get 0.22. Therefore, they are not equal and they are not independent events. Not independent, because the and statement did not equal the probability of each of them multiplied individually. So not independent. All right, let's take a look at number 4. Determine if the events are independent. The probability that it rains on Monday. Probability rain on Monday is 0.4. The probability that it rains on Tuesday is 0.2. And the probability that it rains Monday and Tuesday, Monday and rains on Tuesday, is equal to 0.08. So according to my definition, the probability of your A and B, if it's independent, would be equal to the probability of A times the probability of B. All right, so the probability, nope, I want purple. The probability of raining on Monday and, oops, not that and raining on Tuesday, is that equal to the probability of rain on Monday? Is it equal to each of these separately? That's what we're going to see. Times the probability of rain on Tuesday. We're still questioning it. So the probability of rain on Monday and rain on Tuesday is 0.08. And we want to know, is that equal to each of these probabilities individually? Well, the probability of A, rain on Monday, is 0.4. Probability of rain on Tuesday is 0.2. And if you multiply those two probabilities together, you are going to get 0.08. So yes, they are equal. Therefore, these two events are independent. The fact that it rains on Monday and the fact that it rains on Tuesday. So they are independent events. Okay, independent events. All right, this next one gets a little tedious. So I'm going to erase everything on here and try to get as much space as I can get. So here we don't know what the events are, but we know the probability of A is 2/5. The probability of B is 1/4. And the probability of A and B is 1/25. Okay. Actually, this is not the harder one. This number 6 is the harder one. So, according to my probability of independent events, the probability of A and B, we want to know, is it equal? If it is equal to the other two multiplied, then we know that A and B are independent events. So, is the probability of A and B together, is that equal to the probability of A times the probability of B? Well, we have 1/25, wrong color. I knew that was red. 1/25. Is that equal to the probability of A, which is 2/5, times the probability of the B event, which is 1/4? So, always work down. Is 1/25, is that equal to 2/5 times 1/4? Well, when you multiply these together, you multiply numerator times numerator. 2 times 1 is 2. And denominator times denominator. 5 times 4 is 20. And even if I simplify 2 out of 20, divide by 2 out of 2, I get 1/10. So is 1/25 equal to 1/10? It is not. So A and B are not independent events. I have a lot of birds where I live, so you might be hearing some of that in the background. I like it. Hopefully you can still focus here. Yes, yes. Pretty sure that's a cardinal. Maybe not, though. Okay. All right, here we go. Number 6. Number 6. Oh, this one's not that bad either. I guess it's number 7. I'll just keep pushing it down the way. All right, the probability that you do not get an A on your math test is 0.75. Okay, I gotta make sure I can get all this on here. All right, so the probability of not, that little squiggly sign means not. Some of you forgot that on the last skills check. Probability of not getting an A on your math test is equal to 0.75, 0.75. So if the probability that you don't get an A is 0.75, that would mean the probability of getting an A on your math test, because you either get an A or you don't get an A. That's the full amount of the probability, right? So it would be 1 whole, because 1 whole is the certain event, and we're certain you either get an A or you don't get an A. 1 minus 0.75. So the probability of getting an A on a math test is 0.25. Now they're changing these to decimals, and that's okay. We can still work with decimals. The probability that we get an A on the chemistry test, probability of A in chemistry is equal to 0.3. The probability that we get an A on math and an A in chemistry is equal to 0.075. All right, so I'm going to go down into this next part. So if the probability of getting an A in math and an A in chemistry, is that equal to the probability of getting an A in math times the probability of getting an A in chemistry? So we're checking to see, are these independent? All right, so we can see here the probability of getting an A in math and A in chemistry is 0.075. The probability of getting an A in math is 0.25 times the probability of getting an A in chemistry is 0.3. So the question is 0.25 times 0.3, does that give us 0.075? And if you multiply it out, which you should on your calculator, you should take 0.25 times 0.3, and you will find out, yes, it does equal 0.075. So that means they are independent events. And just a reminder, if you're wondering what are independent events, the probability of getting an A in math class and the probability of getting an A in chemistry are independent. They have nothing to do with each other. So they are independent events. One does not influence or have a relationship with the other. Okay, one more example for today. And this is the one that gets a little tedious. So I'm going to try to go slow. I'm going to erase everything that I have up here. I'm going to probably give myself some extra room. All right. So it says the probability of A is 9/20. The probability of B is 1/2. And the probability of A, given that B happens, is 27 out of 50. All right. So first of all, we know, and there's a couple of different ways you can do this, but I'm going to go from this direction. the probability of A given that B happens, if you remember, it's equal to the intersection of A and B. So that's equal to the probability of A and B happening, the intersection, all divided by, remember this is a conditional statement, so this B comes down here, the probability of B. Okay? That is what we do first. All right. Now, I am just going to manipulate this. Manipulate just means move it around in a way that's mathematically accurate. So if this is equal to the probability of A and B divided by the probability of B, I should be able to multiply both sides by the probability of B. Okay? If I do that on one side, I have to do it on the other. So probability of B's cancel out on the right, and I am left with the probability of B times the probability of A given that B, and that's all I'm writing is what's right here. Probability of B times the probability of A given that B is equal to the probability of A and B. Okay, so let's put this together. We also know, looking at this, what color? The probability of A and B is, if they are independent, the probability of A times the probability of B, if they're independent, is equal to the probability of A and B. All right, so the probability of A is 9/20. 9 out of 20. Times the probability of B is 1/2. 1/2. And the probability of A and B, right here, A and B, I have in terms of this, is the probability of B, and the probability of A given that B. So 9/20 times 1, just putting this together, numerator times numerator, 9 times 1 is 9. 20 times 2 is 40. And we're saying, is that equal to the probability of B? Probability of B over here is still 1/2 times the probability of A given that B. Ooh, just about lost that. A given that B is 27/50. So putting this all together, 9/40. Is that equal to this over here? Well, numerator times numerator, 27, and denominator times denominator, 100. Now I need to see if I can reduce that at all. Factors of 9 right here would be 1, 9, and 3. None of those go into 40. Factors of 27 would be 3, 9, and 1 and 27. None of those go into 100. So they are not equivalent. Therefore, A and B are not independent events. Not independent events. Okay. All right. That was a little intense. Intense as in wigwam and teepee, and maybe even the circus tents. Get it? Intense, wigwam, teepee, circus. Yeah. I'm still punny. All right. So now you should be able to get started a little bit on homework 7.4. This is going to be due, I'm going to say on Wednesday. No, I'm going to make it Thursday. Thursday. Due on Thursday. No. Shoot, I should have kept it Wednesday. I said Thursday now. It's out of the bag. Due on Thursday. Okay. So get 7.4 done. It is on Canvas. Should be linked at the bottom of your Canvas page. Also, reminder, we have the probability test, not a skills check, probability to the test, the last major test of this course is going to be Friday. I think that's the 12th. This Friday, the 12th. Okay. So we will talk about independent events more tomorrow. Finish up talking about it on Wednesday. Start reviewing on Wednesday. We'll review on Thursday for the probability test. And then we'll take the probability test on Friday. Please, unless you are deathly ill, please try to be here at school. It is so important for you to be here, understanding the concepts, asking questions as we're going through the material. Okay? So please try to be here. I appreciate you all being here. And I look forward to being back with you tomorrow. So have a great rest of your day, and I'll see you tomorrow. Bye.